All right. So, welcome everyone. It is great to be with you today. My name is Alicia Duncan. I am the chair of the International. Oh, well, look, there's me on the screen. I am the chair of the International Framework for Nuclear Energy Cooperation, also known as IFNEC. It is wonderful to have this webinar today to be able to connect us, especially since we have a few events uh, coming up on the horizon this year. I want to welcome you to our webinar on AI for nuclear and the virtual tour of the DOME project at INL. I want to thank the INL team for joining us today with their experts to provide us some great information. And this webinar has been designed specifically for the IFNEC community to provide a comprehensive understanding of how AI is being integrated into nuclear technologies, specifically its role in supporting the validation of the world's first microreactor testbed. I'm sure that this session will offer a unique opportunity for professionals and enthusiasts from both the nuclear and AI communities to gain some insight. We will be joined by Chris Ritter for a presentation on AI and nuclear. And afterwards, Curtis Nielsen will take us through a virtual tour of DOME. We will have some time for questions and answers with our experts. And then afterwards, we will provide you with some key logistical and prep information for the upcoming IFNEC Advanced Reactors and Risk Communication workshops happening at INL. So we've got a lot of things packed in this very short time frame together. We might not have enough time to take all of your questions, but I encourage you to please use the Q&A feature to make sure that we can capture your questions and follow up with you after the fact. First, I am very pleased to present the AI and nuclear speaker, Mr. Chris Ritter. He is the Division Director of Scientific Computing and AI and Director of the Digital Innovation Center of Excellence at Idaho National Laboratory. He's founded AI's nationally leading digital engineering team, which grew from 0 to more than 100 and the nation's top researchers and developers in digital science. His team led the first nuclear reactor digital twin, built the Deep Links open digital thread platform, developed the first autonomous non-nuclear microreactor, and is actively building multiple petabyte scale digital and thread platforms. Additionally, he is the Chief Digital Officer of Smart USA. And prior to INL, Chris co founded and led development of the number one cloud native MBSE tool, InnoSlate, used in 107 countries and 2,000 companies around the world. Chris Ritter, over to you.
Thank you so much, Alicia. So we'll pull up the slides. Whoops. Oh, looks like there we go. So we'll pull up the slides and we will present on some of the AI opportunities. Can everyone see the slide deck okay?
Yes.
Awesome. Well, so we'll present some of the AI opportunities in the nuclear energy space. So the U.S. New energy outlook. There's a ton of interest in nuclear energy, and that has led to a lot of different reports that are very relevant in the AI space. So the commercial pathways to advanced liftoff, advanced nuclear report, talked about some of the needs based on the Vogel project in the U.S. and some of the opportunities for improvement, right? When it comes to constructability, making sure your designs are complete before you start construction, and making sure the designs are correct before you start construction. The second report is called AI for Nuclear Energy. Both of these reports are publicly on the internet. This one's on Argonne's website, and you can pull it down. And it's from 2024, but it's funny with AI, it feels like 10 years old now. But chapter one is on nuclear energy. And I think that's because nuclear energy is one of the most interesting use cases that there is when it comes to artificial intelligence and the opportunities to build foundation models that truly have an ability to make a massive impact on the world. And then, of course, our secretary, Secretary Wright, has called for abundant nuclear energy and rapid deployment. On his first week in office, he published this memorandum, and there are multiple references to unleashing commercial nuclear power in the United States, which, of course, has a wide-ranging application to everyone across the world. So we're seeing a lot of investment from what we call hyperscalers in the nuclear energy space. So Amazon has invested in X Energy, which is a Tracer company. Microsoft has invested in 3 Mile Island in the U.S. to basically take an entire unit away just for use of a data center. Google has invested in Kairos Power, a new nuclear startup here in the U.S. And then Meta recently announced an RFI for 4 gigawatts of new nuclear power and is also working on a partnership with Constellation as well. That was in the news. I think it's about a 1 gigawatt partnership there. And these slides, every few days, I have to keep them up to date. TerraPower recently announced an investment from NVentures, which is NVIDIA, the maker of the most popular GPU chips in the world at their company as well. So we're seeing a lot of interest from folks in the AI space, uh, in the kind of nuclear space as well. So it's an interesting harmony that we're getting here. So there are, from my perspective, and this is what we'll spend the majority of our time talking about, three primary opportunities when it comes to artificial intelligence in this nuclear energy arena. The first is, how can we use AI to accelerate the deployment and licensing of new nuclear reactors? The second is how can we qualify new fuels and materials more quickly, right, to bring new technologies to market? And the third part of is probably the most obvious and probably what you thought I would talk about, which is how can we operate those reactors autonomously and what has been our prior experience in doing so? And then lastly, I'm a computational scientist by background, and I think it's really important that as we build these computational tools, we also verify that they work. And one of the best ways to verify they work is build a reactor and try it, right? And so bringing those two components together. So we'll talk a bit with the first. So on the left, you'll see some text and a prompt. And this is basically defining what you want your plant facility to be. So the control room should be 10 feet by 20 feet. The reactor hall should be 40 by 50 feet. And the engineering office should be 20 by 30 feet. You click convert, and you can see that little download. It generates a industry foundation classes file, which is a CAD drawing format for buildings. So what's interesting about this is these are real CAD drawings. It automatically merged the walls together for you. It did a lot of geometric conversions for you. And this technology, this is a video that's now about a year old. We're continuing to mature this technology to do things like equipment placement in those buildings, piping, and other parts of the building structures. So you can imagine only needing to define what you want in your objective and your constraints, and letting the computer do the drafting for you. So it's a very different way of thinking about the problem. If you look at some of the largest projects in the world, which many of those are nuclear projects, it's not uncommon to see hundreds of drafters or hundreds of what we call BIM architects as part of a project. So being able to automate more of that allows us to still retain all that talent that we have in BIM, but to have those people work on multiple projects at the same time to really deploy the power needs that we're seeing, ironically, being caused by artificial intelligence. On the right, we can look at, okay, great, this is a different building, but we can look at another kind of office building. So you can see there's an elevator shaft, there's a railing, and there's 3 stories. So traditionally, when you have a building like this, you'll then take it, right, and you'll mesh it. So meshing, for those who don't know what meshing is, it basically you take that model and you make it simpler that it can be run through a computational analysis. So you can see this basically stick figure mesh, right, where it has columns that are simplified down to a single line. And then it has the floors, right, which have been simplified to a plane. So we're going to take that mesh and then we're going to import it into a traditional industry program. This one's SAP 2000. The analyst is going to look at this and go, I don't want to shake the elevator shaft. So that person's going to remove that part of the model. And then they're going to run a seismic analysis. So all this is happening right within, a few minutes. This process typically, right, if we go all the way to the left of making the actual CAD drawings, making the mesh, and then getting it into a program like SAP 2000 can take many weeks, right, to go through this process. So we're hoping to kind of turn nuclear into what we call in the software space almost like a DevOps approach, where you can really quickly iterate new designs and respond to change much more quickly. Because I always say the only thing that's constant when it comes to construction at this scale is change. And so being able to quickly rectify that change and verify that your change makes sense is super important when it comes to construction. So I've hinted at kind of where we're going with this on the next step, but the kind of ultimate goal is agentic capabilities from an AI perspective, where you have these integrated agents across the design lifecycle and still humans that are doing parts of this that all work together to rapidly iterate a design out. And we recently announced just last week a partnership with Microsoft on the licensing side. So Microsoft has built a tool that does large language models for licensing. And that tool we're adopting at the Idaho National Laboratory to build into our overall ecosystem. And so we're really excited about these commercial partnerships as well to bring in commercial technologies directly into the research enterprise. So the second challenge is autonomous laboratories. So for those who have been to Idaho National Laboratory, you may have been to our sample prep lab or at least seen it under construction. So that building actually has in it robotics, but those robotics are not autonomously controlled. We also, of course, have one of the largest test reactors in the world, the Advanced Test Reactor at 300 megawatts. But what can we do to get more use of those facilities? So first, we can use AI, right, to help control those robotics. And we can bring the time it takes to qualify a new fuel or material down. We can reduce the amount of time we need using these hot cells, right? Which is any small reduction in time is really big when it comes to especially these new microreactor startups that need new materials and new fuels as soon as possible. And then on the test reactor side, right, being able to more optimize the layout of the core with the experiments that we are running in that core. So a lot of nuclear startups, when we present these slides to them, right, I always think they were not going to be very interested in the autonomous labs because this is more a national laboratory thing. Believe it or not, this is an area that there's a ton of interest because there's a ton of interest in accelerating new fuel material qualification. So it's an area that we expect to grow when it comes to the interest. And with the robotic evolution that we're seeing in industry, right, it's a great time to be in the space, right, where we're seeing, new Tesla robotics as an example that are constantly iterating and catch tennis balls in the air, right? And you can kind of see the ability, right, to get more and more autonomy when it comes to national labs for testing. And then the third, and like I said, probably the most obvious challenge is autonomous reactors, obviously moving towards levels of autonomy. We're not going to target full autonomy all at once. So the first experiment we did, and this is actually mentioned in my bio, is our team did the first autonomously controlled non-nuclear microreactor. So this was done in 2022. We controlled what's called magnet, so it's a heat pipe facility fully with AI with no human operator in the loop for about an hour and a half. That test was very successful. There's publications about it, but it was 0.3% off in error rate, and it was a one shot. So the actual thermal properties for that facility could only be tested one time. So they weren't actually able to run that exact same facility more than once. So it was a very impressive experiment, but it was one of those experiments where, as someone who was watching the team when they performed this experiment, that you never knew how it was going to go until you ran that experiment for the first time. And I should mention that of course there were humans watching the AI at all times. Then they could intervene at any point in time, but the AI was actually in control. And then on the right, we did the first digital twin of a real-time, real-world nuclear reactor. This was done with the AGN 201, which is at 5 watts of power, not 5 kilowatts. Very, very small power levels. But it allowed us to do real-time streaming of a real reactor. It allowed us to do AI models, multiple AI models running on that reactor in real time, and to verify that everything worked as expected with red blue team tests. So it did not do control, but it was able to do everything but. And it was really cool because you can see in this animation the control rod drives going up and down. You could actually see all of that remotely. So it was a really, really great experiment to kind of see, the early days of what remote control might look like and the early days of what autonomous control might look like. And that because our models were very accurate, right, that's kind of the first step in getting towards autonomy. And I should mention the control rod drives they're fueled, so they work the opposite way on the AGN 201. So, and the last thing I want to talk about before we get to the last slide is training and design reviews. So one thing that's we'll call it AI tangential, but I think still really important to talk about is, how can we bring advanced visualization technology into the training scenarios? These are really fun when visitors come. There actually is like a narrator that talks to you, and you can kind of hear the narrator in the background, but I'll mute it. But and it's kind of a game, right, for you to learn how to do these things. So you don't get any radiological exposure, obviously, to do this training, and it can scale, right, to a much larger teams to qualify them much more quickly. When we think about the needs for nuclear energy across the world, from more energy deployment, and especially the needs in the United States, right, we're 4xing nuclear. To train and qualify that many operators, we need to be more efficient with the way we're doing it. So this allows us to do that. We also use here on the right AI for design reviews of new nuclear facilities. So this is one of our fuel cycle test beds, and you can kind of see you can do a tabletop exercise where you can actually see the facility. It's really cool, and we've also been able to actually find mistakes in our designs much earlier using those tabletop exercises. So the last thing I want to talk about is the need to verify that this technology actually works. So I think, speaking for myself, I think there's a history, right, of computational folks building really cool tools that stay on the shelf. So how can we work to make sure that we verify the tool's correctness? What is the role when it comes to the national laboratory system and to research labs around the world to see this through? So the Department of Energy put out a request for information looking for data center developers that would like to build on Department of Energy sites. And you can see there an example of just, this is just a script. This isn't a real example of one, but it's just the idea, right, that you could start building data centers on DOE sites with new reactors that perhaps were also designed by AI. And so that kind of concept you could use to verify their correctness. The advanced nuclear reactors, right, of course, would offer reliable connections for electricity. I've heard different people in different countries looking at the idea of doing like a three on, one off scenario, right? So as one's refueling, you could have three reactors that are always operating. Um, and you could get, many levels of nines with being completely behind the meter and not on the grid. So it offers completely new opportunities when it comes to connecting transmission lines. If you talk to those folks, that's actually still a big challenge when it comes to data center developers, is not just getting the power, but getting the power to them. So the generation is one part of the problem, but of course transmission is the other, and that can solve some of those issues. And so really we're looking for commercial partners that are interested in building these kind of AI designed, autonomously powered AI data centers, perhaps using DOE sites and facilities. So I will send it back to you, Alicia. Thank you for your time, and we will have time for questions here in a few minutes.
Thank you so much. I really appreciate that. And I think since we are well ahead of schedule, that we should see if we have a few questions now instead of going to our next speaker right away. Could we
Oh,
check
love it.
in and see if we have any questions? I can't see the hands, but maybe we have no questions. Do we, anyone have their hand up? If we cannot see your hand, please just unmute yourself. Okay. Well, then we will move right along. Thank you so much, Chris. And we'll have another opportunity for folks to, oh, we have two hands. Okay. So let me check and see quickly. I see a hand from Eduardo. Eduardo, please go ahead.
Thank you. Can you hear me?
We can hear you great.
Okay, well, thank you. Good morning, everyone from Asunción, Paraguay here. Thank you for your presentation, Mr. Ritter. I was wondering if you're at freedom to share with us what kind of codes you use for these simulations.
Yeah, that's a great question. So Idaho National Laboratory has a long history in development of the moose ecosystem of animals. You might be familiar with moose. So that's one of our largest ecosystems of codes that the Department of Energy has invested in over the years. Another ecosystem of codes is called Deep Links. Both of these are available on GitHub, by the way. which is used as the central framework for most of these digital twins and digital engineering applications. So right now we're in the midst of publishing what we call Deep Links Nexus. So the current Deep Links that is out there publicly, that's what I would call Deep Links Classic. And the new version is coming out actually in the next couple months, which has been moved to microservices to allow more people to develop with it. And all this is connected. This is all one ecosystem of tools, right? So the Moose ecosystem is our first principles tools. Deep Links is really our data platform for connecting these things. Our AI models, unfortunately, are not fully open, but the publications are. So you can look at if you look at like Magnet Digital Twin, you will find those publications online. We also have publications about the AGN 201, in fact, quite a few when it comes to that digital twin and how we did it and what our results were with using a multimodal AI. So hopefully that helps answer with what's out there. And of course, we're happy to talk anytime offline and provide more information.
Thank you, sir. Thank you.
Thank you kindly. I see another hand. I hope I pronounced your name correctly. I saw Huda. Maybe the hand just went down. Huda, did you have your hand up? Okay. The hand's no longer up, and I don't hear her.
I see a chat for Nicholas in the Q&A. Should we want me to answer that one?
Oh, okay. Now he has his hand up as well. So why don't we go there? Nicholas?
Hello, can you hear me?
We can hear you
Yes.
great.
Yeah, so not an AI specialist here, but just a quick question and curiosity. So how do you intend to train the AI engine in regards to operation and maintenance of the reactor?
That is a great question. So for the AGN 201, we were able to do real-time streaming. Interesting, the AGN, because it is a student, primarily used for student training, you get a lot of you get a lot of variability. It's not just running right at standard operations, right? So it was a really great reactor where we were able to run many different experiments before we actually did the red blue team test. And so anyway, so the key hard part of that, by the way, and it's worth mentioning, is they had a logbook, which was, and hopefully this isn't the case for many of you, was all on paper. And we found out that logbook wasn't very useful. The data that was being captured wasn't indicative of the same data that the AI model was going to see. So we didn't really use much of that when it came to actually building the data-driven models. Most of the data that we used was data that was captured from a historical sense when we had it connected to our cloud tools. So we had a tool that was aptly named Jester to ingest the data coming from that reactor in real time, and then kept streaming that data through all these different experiment studies that the students were running. So when we actually ran our real test, right, that model had been trained on quite a bit of historical data at that point. Keep in mind, all of this was done within a 1-year time step. In fact, the final experiment was, I think, done in month 9 or 10. So, we probably had about 6 months or so of data to look at that point. But it wasn't 60 years of data or anything like that. Now, maybe some of you have historical data that's already been digitized, right, and in better format. And of course, as you know, with machine learning, more data is always better because models trained. There's a friend of mine who always says models trained on no data are just imagination. So anyways, from an AI data-driven perspective, of course, our physics models, right, we were able to use those logbooks to start training or start building, I should say, not training our physics models. And the AGN 201 model used both a physics and data-driven model, both at the same time. The magnet model eventually did both as well, using a physics-based and a data-driven model. And sometimes we'll even do 3 different models, one that's like an anomaly detection model as well, all running at the same time. Hopefully that answers your question. Are there any other questions, Alicia?
No, sir. And we will have more time later in the set time for the Q&A. And so I really appreciate your insightful presentation. And we might have some more for you in a few moments. Thank you again. So if we could next have Mr. Curtis Nielsen lead us through the virtual tour of NRIC's Dome project. I'm also very excited to hear about this one as well. Mr. Nielsen currently serves as NRIC's NRIC's technical program manager responsible for the dome ecosystem and helping NRIC with new and irradiated fuel management, ensuring timely and efficient delivery of dome and the projects that will support the next generation of advanced reactors. Prior to NRIC, Curtis worked 16 years at the Naval Reactors Facility in spent fuel packaging and storage and program management. Curtis, thank you for joining us today. If you would go ahead and get us started, I turn the floor to you. Thank you so much.
Hey, thank you, Alicia. Hopefully you can see my screen here.
Yes, we can.
Okay, thank you. All right, so thanks for the introduction, Alicia. I'm going to start with a virtual model and fly through of the dome facility, and I'll pause it and talk about certain aspects of the facility. Just some background before I start it. The dome facility is currently the only advanced reactor test bed for these Gen 4 advanced reactors that we plan to test in the United States. The facility has a design capability of up to 20 megawatt thermal and less than 20% enrichment. Today, most of those reactors that we have lined up, we partner with different industry partners. Those reactors today are all currently designed as TRISO-based reactors. And so a lot of our safety basis and our learning is based on that fuel type. So that I'll give that as a background. I'll start here through this fly through. This is the dome facility, which you can see is obviously the dome shaped. It's the containment building that used to be the experimental breeder reactor number 2 facility. And for obvious reasons, we want to have a containment building to test these reactors in. This is looking east on that facility. This is out at the Materials and Fuels Complex on the Idaho National Laboratory. And we chose to use the EBR2 facility as dome, and we're currently under construction with the facility to upgrade most of the utilities and make sure that we have all the needs that we have for the facility. One other thing I'll mention associated with AI, all of our facility has a digital twin at this point, and we have required anybody that wants to do an advanced reactor test in the facility that they have a digital twin as well. And we ask that they share that with us to make sure that we integrate it into our AI learning of those digital twins as we get into this. And I'll talk more about how we're leveraging AI alongside of these advanced reactor testing, as well as the construction of the and upgrades of the facility we have. So I'll start the tour here. All right. As you can see here, I'm going to pause. We have different penetrations that go inside of the dome facility. Each of these serve different purposes. I'll start here with this on the right. You can see this penetration is primarily for heat rejection and facility services that the dome facility itself needs. Most of these are cooling and electrical systems that are feeding instrumentation for the facility itself. As you can imagine, the dome facility has a need to get a lot of information, especially with these advanced reactors, and what are the facility conditions itself. So this one primarily is used by the dome facility. It does have some capabilities for the developers to plug into and use their own utilities or tap into existing utilities that we have, things like site air, compressed air, or even water. I'm going to continue to fly through the yard here, as we call it. As you can see, we have an infrastructure of different types of things that are needed here for doing advanced reactor testing. We have a single bank of radiological ventilation for the facility and capabilities to bring in more if we need to. Same with our heating and ventilation. We have a duct bank here. And also, if needed, we can expand that to support larger tests as needed. We built this yard with the bare minimum in mind, but the ability to expand. And some of these things, we also left space for developers to go put some of their own utilities in if they have a need for that, and try to be flexible as we can. All right, continue to fly over the top of the yard. A couple things I'll mention here. We do have a ventilation control system. This little building here on the bottom right, that has the controls for all the heating, ventilation, and cooling for the facility. This does have tie to an integrated control system or control room inside. Again, this is one of those that we are trying to get as much data as we can and begin training our AI as we get that fabricated, working with the vendor for the HVAC as well. You can see here we've got a couple different electrical boxes, panels, transformers, etc. that we have. And we also have space just to the north here. To the east, west of the facility. We have laydown areas that we can have the developers bring in their own containers that if they need to have their own auxiliary control room, or if they need to bring in things like a heat exchanger or something that they might need for their own experiment, they can bring those into the yard and set those and hook those up to this infrastructure that we have here. Lots of tray runs of electricals. I will mention that many of these we left space and empty, again, for the developers to bring in their own componentry and electrical runs to support their needs. I'm going to talk about another set of penetrations here. If you can see my cursor on the right here, you can kind of see these blocks. These are the electrical and instrumentation penetrations that we have within the facility. With these advanced reactors, there's a lot of need for understanding how the reactor is operating during the experiment and gathering as much data as possible. This is not just for the qualification of the reactor itself, but it's also many of these developers are new startups. They understand the importance of gathering the data and learning how to get these reactors to be at least remotely operated. Autonomous is the goal for many of them. And they know that the data is the key to get that information. So we have several penetrations, and right now these are modeled just as blocked out items. These are just the stubs that we have on those to maintain the containment structure of the facility. The developers we have design interface for those that we provide at the beginning of our collaboration with those industry partners, and we work with them on modifying those as needed. I'm going to move over to these developer penetrations. These are very large penetrations in the dome facility. These are 40-inch diameter, and they can be multi-purposed, however the developer needs. Recently, the Department of Energy announced that the first two developers that will be in the dome facility are Radiant and Westinghouse for their individual advanced reactors. And both of these developers have already got plans for the use of these penetrations, and it's a mixed use. Both developers have identified that they want to bring out heat transfer activities for use in exchanger, lots of instrumentation. Again, even with all these electrical penetrations, there's still a need for more information and instrumentation penetrations. So that's one of the uses for these two penetrations here. Okay, I'll continue to fly over. This is our main hatch into the dome facility. This is where the reactors, generally they'll be received in shipping containers or something like a shipping container. They'll be placed on this large pad here, and then they will be orchestrated into this large hatch, as we call it, into the dome facility. We're going to fly through that here in a second. As we go through this hatch, we enter into the dome interior. As you can see inside of here, we've got a couple of shipping containers modeled up. One's a 20-foot, one's a 30-foot. This facility is essentially an 80-foot diameter interior space, and it's 80 feet tall. One of the things I'll say here, we don't have everything modeled yet into this. That's one of our ongoing efforts to make sure that we have the latest BIM information pulled into this as we continue to fabricate and install equipment. But a couple things that I'll point out here. Overhead, you can see a overhead crane. We call it the polar crane, that can rotate completely around, and then it has its own bridge and trolleys, so you can place heavy objects within the facility. We also have a large interior ventilation system. One of the goals that we have with the containment is half of our thermal capacity is actually stored within the facility itself, and that helps contain the facility. We also have different ventilation running through it, radiological ventilation stacked on top of the regular cooling. And then we have different utility services. This is a water tank that we have. And then one of the things that it looks like there's a lot of space, but we know there won't be. One thing not modeled here yet is the operational shielding that we'll have over the top of each one of these advanced reactors. That's not modeled here, but that will take up a significant amount of the floor space that we have within the dome facility. All right, just going to kind of look around here. You can kind of get a sense for the space as it is. And this also gives us a chance to look at the penetrations I talked about, the interior penetrations. Like I said, the utilities and the dome facility penetrations are here on this area. Again, these blocks are the electrical and instrumentation penetrations that I talked about. And again, we have these just modeled out as blocked out penetrations. One of the things that there'll be several runs that come out of these and likely on the floor or through different locations that go through the shielding. And that's one of the complications that we have today in making sure we get that electrical and instrumentation fed to the reactor without interference from the operating reactor itself. And then, let me go back a little bit more. The last thing I'll show here is the large developer penetrations. These are the 40-inch penetrations. Again, you see they're right near where the reactors will be, and the developers can use whatever they need to for those penetrations themselves. And then I'll just do the fly out of the facility. Again, it's meant to be a very flexible facility to make sure that we support the needs of the different developers and support what they have and their information needs. Now, I'll talk just a minute about how we're integrating AI into the dome ecosystem, as we call it. First thing, we're making sure that we're integrating AI into the digital twins and pulling data into the AI, so we have a single source of truth to accelerate. We're focused primarily on the authorization of each of these reactors. And some of the things that we're doing is we're using existing documentation or authorization basis documents today to train that AI so that it can help generate that regulatory document based on the models and then spit it out in a way that the regulators recognize the format because it's learned from existing authorization documents. The other thing that this AI project for Dome is doing is we're using it to go identify potential issues or errors with some of the designs. As you can see there's a lot of complicated penetrations. There's many penetrations, and we're using AI to go lay out how would that work, especially as each of these advanced reactor developers provides us more CAD models and digital models of what they plan to go do within the facility. It can help us identify those at a much faster rate than a large group of engineers can. And then in the end, one of the future goals for the AI use in Dome is that we want to use AI to probe more into the GUI interface for the reactor operators and for the regulators of how to make things more reviewable, actually interface directly with the models of the reactor as a way to go review the reactor design for DOE authorization. And that is any questions?
Thank you so much for your presentation. I don't know that that's been done before. And so I feel like we've been the first to receive this wonderful presentation. You're shaking your head. Yes?
Yes, I think that's the first time we've done a fly through like that and talked about AI. So.
Woo! Okay. So this is exciting. Thank you so much. Let's see if we have any questions on this. And while we're waiting for folks to not be shy, I will take the opportunity to ask the country's representative IFNEC members to check into the chat and tell us which country you're from. And I also want to give a shout out to the U.S. colleagues who've joined. I see NRC, NNSA, IA, State Department, and I know I'm forgetting somebody, and I apologize in advance. I see some DOE-NE colleagues as well. But all right, we've got a question. I knew if I talk long enough, someone would ask. So Dario asked a question, and he said, what do you think the cost per megawatt would be to build a microreactor like this?
Yeah, good question. I think it depends on the technology and the type of each one of these startup companies. And we haven't built any yet, so I couldn't give you a number. I will say that the cost range is very wide right now because they're still fairly low technology readiness. I think we'll have our first good sample set by the end of 2027 when we get through testing both the Westinghouse and Radiant advanced reactors. So I couldn't give you a figure now, but there is, we're working through that information today.
All right, thank you. Do we have any other questions? And if you want to, I don't see any hands, but if you can't manage to get your virtual hand up, you could unmute yourself. And thank you to Canada for checking in. All right, well, I don't see any additional questions. Curtis, thank you so much for this look into Dome. This is exciting, and we appreciate the opportunity to be able to see it. So thank you so much. I appreciate you.
Thank you.
All right, so we will keep moving on and move on to the next part of our agenda. And with that, we will. And let me give the AI presentation one more opportunity as well. Are there any questions from the AI presentation that you may have thought of? Going once. Okay. So gentlemen, if you would like to drop off since we don't have any more. Uh-oh, there's a hand. Jorge, Please, sir, go
Hi,
ahead.
hi, Alex.
How are you?
Just one question. Are you planning to use the AI to control the reactor itself, not only in the helping of building, as you are showing, but just let the AI control the whole reactor in the control room, let's say,
The short
in the
answer is
near future?
yes, right? Over time, right? Starting on short duration experiments. As you talked about during the first presentation, we've already done AI control of
Yeah.
non-fissile reactors, so we're continuing to mature
And,
that technology.
and what about the regulators? Because I think it must be in the
Yeah, it'll be a
to
close part of that journey, right? It will be a journey. It will not be
yeah,
one ChatGPT will not be running, will not be controlling a reactor, at least in the foreseeable future.
yeah.
And there will be a lot of regulatory interface over
But
that.
you started the process with the NRC, right? Or not
We,
yet?
we are still in the very early phases of autonomous control, right? I think that the way we see it, right, is growing levels of automation. Again, probably the very first autonomous controlled experiment will be done, for a short duration, like we did with the non-facile experiment, right? Through DOE authorization, which remember in the US we have DOE auth and we have NRC, and then continue to scale up that technology over time. Um, so, so yeah, we are actively talking with the regulators, and there are pathways to do this, but we are not planning on autonomously controlling a reactor, in the next year or anything like that. That's a
Yeah.
long.
Yeah,
Just
and I'll
one last question. Sorry. Sorry. It's only for microreactors, or are you planning to do that with SMR as well?
So I think the highest value, right, from an economics perspective, is in the microreactor space, and that's likely where we will start. That's where we're seeing the most interest from our industry partners. Of course, if it works for microreactors, right, we might see that technology transition over to SMRs and larger facilities. But that is our current approach, right, is to start at the smallest power levels and kind of grow on power levels over time. So that's where we currently are.
Okay. Thank you very
yeah,
much.
Yeah.
and I'll just add one thing too. Thanks, Chris. With the dome reactors, obviously, as you heard me talk about, the main thing is to build the confidence in that AI. How do we learn from it? And then how does it help us with the authorization aspect? And that's part of the reason that we're doing the experiments in the dome facility with these microreactors. It gives us that actual runtime, the ability to do, I'll say, semi-remote activities. And so you're doing building blocks to get to that point. As Chris said, obviously in the next year, 2 years, there won't be any of that autonomous control. We just need to have the data and the confidence first and work with our regulators.
Well, gentlemen, thank you both. I really appreciate your very interesting and unique presentations. I think it is really an opportunity for us, even in the United States, to be able to see and witness these things and hear about these groundbreaking efforts. So I want to give you a big round of thanks, as well as Bonnie Hong, for organizing these presentations for us. And obviously, again, to our colleagues from the US who joined us today. As we get ready to move into the IFNEC presentation, that will talk to the logistics that will happen at the Idaho National Laboratory, our workshop that we will have on advanced reactors and risk communication. This would be a time for those who are not IFNEC members. You could drop off if you wanted, because we're going to be focused specifically on that event that we will be hosting at Idaho National Laboratory. Again, I thank you for joining us, and I thank those who checked in. I actually tried to reply back to you, but I think I was only replying to the host and panelists. So I definitely saw Canada, Nigeria, El Salvador, and I know Paraguay is on the line because you all asked a question. Thank you so much for you taking the time to join us from so many countries. And I want you to have that same enthusiasm as we prepare to welcome you to INL. So without further ado, I'd like to turn the microphone to Ms. Soyoung Jung and have her run us through the logistics for the Idaho event. Thank you. Over to you.
Thank you, Chair. Good afternoon to you all from Paris. Thank you all for staying for the final segment of today's webinar. I'll now quickly walk you through the key logistical details of the IFNEC Advanced Reactors and Risk Communication Workshop. Just some quick stats for everyone. Over 50 people have registered for this event from over 20 different countries, and we are excited to see such a strong engagement as we get closer to the registration deadline, which is just next Friday, August 1st. The workshop runs from October 6th to October 9th this year, and the sessions will be held at the Idaho National Laboratory in Idaho Falls, Idaho. Participants are advised to arrive on Saturday, October 4th, to avoid any issues due to flight delays or cancellations. An excursion to the Grand Tetons is also scheduled for Sunday, October 5th, providing a good opportunity to connect with fellow participants. Please mark your calendar accordingly for the main dates. The nearest airport from the venue is Idaho Falls Airport, with direct flights from 5 different cities. One important thing to note is that from October through February, United Airlines flights in and out of Denver have been canceled occasionally due to winter weather conditions. Such cancellations may cause a delay of up to 14 hours to get on the next flight into Idaho Falls. Therefore, we recommend that you review the flight delay and cancellation history before finalizing any of your bookings. For the hotels, we recommend these 3 hotels, including Hampton Inn by the airport, Hilton Garden Inn, and TRU by Hilton. Transportation between hotels and the INL is provided by INL bus service with pickups at both Hampton Inn and the Hilton Garden Inn, which is located right next to the TRU by Hilton. Kindly also note that Idaho Falls does not have regularly scheduled public transportation, and taxis and Uber services are highly limited in Idaho Falls, especially outside the airport area. So please arrange hotel shuttle pickup in advance, as hotel shuttles tend to be the most reliable option. As an alternative, you may consider using a ride-share service called the Greater Idaho Falls Transit or a private travel company. For the meals and dining, coffee, lunch will be provided each day of the meeting, and local downtown restaurant options within walking distance of the hotels have also been provided for the registered participants. And for the visitor documentation, just a reminder, international visitors need to submit the required documents at least 45 days before the visit. The required documents include digital copy of passport, digital copy of visa, CV, bio, and recent photo. The visa can be sent at a later date if not yet received. Please do not forget to include information about dietary needs, Bluetooth medical devices, and physical limitations when you register. Kindly also note that official invitation letters from IFNEC to support the visa process are also available upon request. For the facility access and dress code, we recommend wearing long pants and closed-toe, closed-heel shoes. Please be sure to choose comfortable shoes, as there will be a fair amount of walking. For advanced test reactor visits, natural fiber clothing such as cotton is strongly recommended. We also recommend avoiding excessive metal, as it may cause delays during security checks. And for regular sessions, business casual attire is recommended. Please also make sure not to bring any of the prohibited articles listed here when going through the batching process. Laptops, mobile devices, and smart watches are not allowed in some facilities. And photography is generally not permitted, but if in need of a specific photo, please request it from your host. October temperatures in Idaho Falls range from 30 degrees Celsius to 14 degrees Celsius with 3 to 8 days of rain and occasional snow. Please check the 14-day weather forecast before arrival. And again, please dress in layered clothing to accommodate for the expected weather. We are also planning to organize a ceremony on the margins of the workshop to recognize countries that have newly joined IFNEC as an observer or a participant country. Kindly note that newly invited countries first hold observer status, and then an observer country can become a participant country by officially endorsing the IFNEC statement of mission. To this end, a letter to the chair of the steering group copying the technical secretariat is needed. Please do not hesitate to reach out to the IFNEC secretariat to learn more about this process. And you will be able to receive all the logistical information, list of dining places, as well as the IFNEC terms of reference once you register to this workshop. And please feel free to reach out to IFNEC secretariat if you have any questions or require any assistance from us. Thank you for listening.
Thank you, So-Young, for that presentation. I'm glad to see that we've had such an informative time today in this very short hour that we spent together. I do want to be very clear. The deadline is fast approaching to get those security forms in for the Idaho National Laboratory. That is one part of this that we cannot control. So if you still have not received your approval, I would still encourage you to get those forms in because we unfortunately will have to comply with Idaho's timeframe for processing and we'll need your cooperation. I want to thank you all so much for joining us today. This was so much fun for me. I will be ready to announce another one in the next few weeks so we can learn about another fun topic together and see some of the cool, exciting innovation that we have going on in the United States. And happy to also do some sort of webinar where we can learn about what's happening in your country. If you have interest in sharing something with us, we would welcome that. And you can feel free to reach out to me or the IFNEC Secretariat. And I'd like to end with a note of thanks to the NEA Technical Secretariat, as well as my own team, Lebra Anusha Ramaswamy, who serves as the U.S. side of Secretariat oversight, as well as the INL folks one more time, and all of you, our special guests who have joined us from around the world. So thank you so much, and I wish you a great rest of your day.